Hello, this is John Miares, and in this video, I want to take a look at a couple of items that we skipped over when we looked at section 6.2 before that are going to become important as we progress through section 6.3 and the rest of the unit. You might be wondering why I didn't cover this stuff when I was teaching the rest of section 6.2. Well, that video was already long enough, and I didn't want to give you information overload, so my preference was to wait to teach this material until later after you've had a chance to digest the information from the rest of section 6.2 more thoroughly. There's only 10 slides total in this presentation, including this title slide and the slide with the problem challenge problems on it, so it shouldn't take too long to go through, I hope. This section focuses on two special triangles that seem to come up a lot in various problems in pre-calculus and in calculus, primarily because doing computations with these triangles tends to be much simpler than with others. Consequently, these particular triangles happen to show up a lot in various examples we're going to be doing both in this course and the next. The first special triangle we're going to look at is called a 45-45-90 triangle, which is also referred to as an isosceles right triangle. We call this an isosceles right triangle because it is a right triangle that has two equal side lengths, specifically the legs. What you're going to see is that yes, these legs have equal length and we can call them x, and the hypotenuse has length that is a square root of 2 times the length of either leg. We can prove this relationship by applying the Pythagorean theorem. We know we have a squared plus b squared equals c squared, which if we know the lengths of the legs are equal, and we can call them both x, so we have x squared plus x squared equals the hypotenuse squared, which simplified becomes 2x squared equals the hypotenuse squared. Taking the square root of both sides gives the hypotenuse equals the square root of the quantity 2x squared, or taking out the perfect square leaves us with x times the square root of 2. Let's look at a couple of examples of how we might use this relationship to solve for missing side lengths in a 45-45-90 triangle. Suppose you're told that you have a 45-45-90 triangle with legs of length 6 and you want to find the length of the hypotenuse. Well, if the hypotenuse is the length of the leg times the square root of 2, and we know the legs have length 6, then the hypotenuse will have a length of 6 times the square root of 2. We could also try to solve this out using the rules of SOHCAHTOA. Knowing the leg is 6 and the hypotenuse is unknown, we could say that the sine of 45 degrees, or for that matter, the cosine of 45 degrees, equals the leg length 6 over the hypotenuse. Looking at this triangle, we can see that the ratio of the opposite to the hypotenuse will give you x over x root 2, which reduces to just 1 over root 2. So we could write it as 1 over root 2 equals 6 over h, which then if we cross multiply gives us the hypotenuse h equals 6 times the square root of 2. Let's try a variation on this. Suppose this time we know the hypotenuse is 10 and we want to find the lengths of the legs. We have a couple of approaches we could do here. We know that the length of the hypotenuse is the length of the legs times the square root of 2. So we could divide 10 by the square root of 2, then rationalize the denominator to get 5 square roots of 2. We could also use SOHCAHTOA to solve this out as well. We could say that the sine of 45 degrees is going to be the opposite side, x, over the hypotenuse 10. We figured out earlier that the sine of 45 degrees had to be 1 over the square root of 2. So we can set that equal to the fraction x over 10. Cross multiplying gives the square root of 2 times x equals 10, which we can then divide out to get x equals 10 over the square root of 2, which again will rationalize as 5 times the square root of 2. The other triangle we see a lot is called a 30-60-90 triangle, and its roots come from taking an equilateral triangle and cutting it in half. So we have this equilateral triangle here that has 3 equal side lengths and 3 equally sized angles measuring 60 degrees each. When we drop an altitude from the top, that altitude does a few things special here because it's an equilateral triangle. It will divide the angle in half up top into two 30-degree angles, and it will divide the base into two equal halves. So now we have what was an equilateral triangle split into two congruent triangles where the angle measures are now 30 degrees, 60 degrees, and 90 degrees. Let's say we label the short side of those triangles x. We'll put that here. This makes the entire base of the triangle, starting from here, going all the way into the corner, as 2x. Consequently, each of the hypotenuses is going to be 2x here and here. Suppose we wanted to find the height of this triangle, marked by the dashed altitude in this figure at the top right. We could use the Pythagorean theorem. This says a squared plus b squared equals c squared, and then we can plug in what we know. We have the short leg in this 30-60-90 triangle having a length of x. The hypotenuse will have a length of 2x, but we just don't know what the height is. Squaring out the 2x will give us 4x squared on the right, which we can then move the x squared on the left over to the right to get the height squared equals 3x squared. Then we can take the square root to get the height equals the square root of the quantity 3x squared. Simplifying the radical gives a height of x times the square root of 3. So here's our relationship here. You have a short side of this triangle, which we can label x. We have a hypotenuse, which will be 2x, which will be double the length of the short leg. And we have a height, or long leg, which will have length of x times the square root of 3. Here's a couple of examples to try. Find the lengths of the two legs of a 30-60-90 triangle whose hypotenuse length is 10. Just like before, we can look at this from the proportional view or from the SOHCAHTOA view. We know the hypotenuse has a length of 10, and the hypotenuse is double the length of the short leg, which means the short leg must be 5 units long. From here, we know that the long leg is the square root of 3 times the length of the short leg. So the long leg is going to be 5 square roots of 3 units long. Coming at this from the SOHCAHTOA perspective, we could say that the cosine of the 60-degree angle, the short side, is always going to be half the length of the hypotenuse. Then the cosine of 60 degrees is going to reduce to 1/2. We can say 1/2 equals x over 10. Cross multiplying will give us 2x equals 10, or reducing x equals 5. You can then either use the Pythagorean relationship or other means to establish that the long leg will be 5 square roots of 3 units long. Now suppose you wanted to find the length of a hypotenuse of a 30, 60, 90 triangle whose longer leg has a length of 6. Based on our diagram, we could set x times the square root of 3 equal to the length of the long leg, which is 6. Then we can divide both sides by the square root of 3 and rationalize our denominator to get x equals 2 times the square root of 3. Now, the value of x is actually the length of the short leg, but the hypotenuse is just going to be double the short leg. So we can multiply that length by 2 to get the hypotenuse having a length of 4 square roots of 3 units. Alternatively, we could use SOHCAHTOA to say that the sine of 60 degrees in the corner will equal the opposite side 6 over the hypotenuse h. Knowing what those lengths are generally supposed to be in a 30, 60, 90 triangle, we could turn the sine of 60 degrees into the square root of 3 over 2, which is x root 3 divided by 2x with the x's canceling, and set that equal to 6 over h. Cross multiplying gives us the square root of 3 times h equals 12, which when we divide by the square root of 3 and rationalize gives us the hypotenuse equals 4 times the square root of 3. Often when looking at these special triangles, we don't care so much about the x's and we just look at the proportions for the side lengths. In any 45, 45, 90 triangle, for every 1 unit that the leg is long, the hypotenuse will be the square root of 2 units times as long as it. So we often will drop the x's and label the sides with how those sides break down, which would be 1, 1, and the square root of 2. Similarly, in a 30, 60, 90 triangle, we could label the short side as 1, the hypotenuse as 2, and the height as the square root of 3. And every 30, 60, 90 triangle that is similar to it will have side lengths that fall into these proportions. This is what can be used to quickly evaluate the various trig functions associated with these angles. The sine of 45 degrees, opposite over hypotenuse, will always reduce to 1 over the square root of 2, no matter how big or how small the triangle becomes lengthwise. The cosine always reduces to the same thing because the two legs have equal measure. The tangent of 45 degrees, opposite over adjacent side, will reduce to 1 over 1, which is just 1. In a 30, 60, 90 triangle, the sine of 30 degrees becomes the opposite over the hypotenuse, which becomes 1/2. This will be the same as the cosine of 60 degrees. The adjacent side over the hypotenuse will also reduce to 1 over 2. Looking at the cosine of 30, which will be the same as the sine of 60, the ratio will reduce to the square root of 3 over 2. The tangent of 30 degrees, opposite over adjacent, will look like 1 over the square root of 3, which rationalizes to the square root of 3 over 3. And the tangent of 60 degrees will equal the square root of 3 over 1. Let's say I asked you to evaluate these expressions without a calculator and to provide an exact answer, not a decimal equivalent. We could look at each triangle and see what the relationships to each of the side pairs is going to be, knowing that all 45, 45, 90 triangles are going to degenerate to having the side lengths with ratios 1 to 1 to the square root of 2. And all 30, 60, 90 triangles will have their side lengths reduced to ratios of 1 to the square root of 3 to 2. To find the cotangent of 30 degrees, we'll look at the 30, 60, 90 triangle on the right and come at it from the perspective of the 30-degree angle. The cotangent is the adjacent over the hypotenuse, which then becomes the square root of 3 over 1. For the secant of 45 degrees, we want to look at the triangle on the left-hand side and look at the ratio of the hypotenuse to the adjacent side, since the secant is the reciprocal of the cosine. Doing that here gives the secant of 45 degrees equal to the square root of 2 over 1. The cosecant of 45 degrees is going to be the same thing because here we want to take the hypotenuse over the opposite, or the reciprocal of the sine, to get the square root of 2 over 1. Finally, for the secant of 60 degrees, we want to take the hypotenuse of the 30, 60, 90 triangle, divide it by the leg adjacent to the 60-degree angle, and this is going to reduce to 2 over 1. Now let's try doing a few of these backwards. If you're told you have the cosine of theta equals the square root of 3 over 2, this will become a 30-degree angle because when you look at the 30-degree angle in the right-hand triangle, the adjacent side has a length of the square root of 3 and the hypotenuse is 2. If you want to know what angle has a tangent value of the square root of 3, you're trying to figure out which angle is showing an opposite side of the square root of 3 and an adjacent side of 1, which is implied by there not being a denominator in the given fraction. Looking at these triangles, it has to be 60 degrees. Now, where the cosecant of theta equals 2, you have a ratio of the hypotenuse to the opposite side is going to equal 2, or 2 over 1. That's got to be for a 30-degree angle. Lastly, we have the secant of theta equals the square root of 2, which reduces to really the square root of 2 over 1. Given our choices, it should be clear that it's going to be 45 degrees. Now, there's a few examples in section 6.2 that are a little more complex, and if I had written this textbook, I probably would have put these problems in their own section. Let's look at this one. Suppose we're given this diagram and we see that segment BE has length of 2 and the angles are given as shown. We want to find the lengths of all of the individual segments of each triangle in exact form, which really means simplified radical form. Well, we know segment BE has length of 2, so let's label that here. If I look at this diagram carefully, segment DE is going to be the hypotenuse of the 30, 60, 90 triangle labeled DBE. Given that DE has to be double the length of side BE, which means that DE has to have a length of 4, which I can now label here. Now looking at triangle ABE, side BE is the long leg of that one, and side AB is the short leg. So we could say that segment BE is the square root of 3 times the length of AB, which will divide out as AB equals BE over root 3, which after rationalizing gives us a length of segment AB as 2 root 3 over 3, which I can label here. Now BC is going to have the same length as AB because segment BE splits the equilateral triangle in half. So that makes BC also equal to 2 square roots of 3 over 3, and we'll label that side here as well. Looking to the far left, segment AE is the hypotenuse of triangle ABE. So if the short leg is going to be 2 root 3 over 3, then segment AE must be double that length, which becomes 4 root 3 over 3. Along a similar line, side length CE will have the same length as side AE, so that must also be 4 root 3 over 3. Now, the only side missing that we have is side CD. It doesn't look by itself that it is part of any of the 30, 60, 90 triangles, but if you look very carefully, triangle DCE is an isosceles triangle. Angle DCE is 120 degrees, which will only leave you 30 degrees for angle CED. So if that triangle is isosceles, then side length CD has to have the same length as CE, which will make it 4 root 3 over 3. There's a few problems like this on the homework that you'll have the chance to play with. So if you have any questions, we can certainly take a look at them in an upcoming ORT session. Okay, that's all I wanted to cover from this section. As I said in the beginning of the presentation, these triangles show up a lot in our further study, so it's good to take some time to look at these separately from everything else. Knowing how these triangles work is going to be critical as we move into section 6.3 and beyond, so it's probably best to get a head start and look at these problems now. Here are the problem challenge problems for section 6.2b. Give these a try and see what you think. If you have any questions, we'll be sure to go over them in an upcoming ORT session. But you can always email me, or better yet, put your questions up on the discussion boards. Thanks for watching, and we'll see you all soon.